Lovely day. Do I have some slides? I want to show you this. This is everything. There will be other slides, but this is everything. Without plasmas, we would be completely in the dark. These people are in the dark. And I think the idea is that if you're in the dark, bright lights there, you can't see, and also you don't know. You have no knowledge if you are in the dark. So let's go. Does this work? Wait a minute. Wrong button. Okay. We're going on a journey through time. Time begins here. The Big Bang, 13.8 billion years ago, and it ends, at the moment, it ends here, which is now. Now, some time ago, not back there, but sometime back here, we did this with electricity. Electricity is going to be important to the story of plasmas. We can't do this now, it's not allowed. This is a small boy. These are ropes of silk. And here's a small girl. They're holding hands. That bit is okay. This is a machine that makes electricity. And it passes through the boy to the girl who picks up pieces of paper. This is electricity, it's electrostatics. This was in, some date. This was in 1748. Now, in 2026, last week, this is my grandson. And he's going to go down. Oh, no, he's not. He's going to go up. Oh, wait a minute. Can I go backwards? Yes. Can I make that film work? There is a film here. Can you click on the screen? Here he goes down the slide. Watch. Look at his hair. That is electrostatics. They showed me this film last week, and I said, please, I want this for my lecture. I take it to Ukraine. So I did. I also asked the permission of the parents, and they said it was okay. We are going to go on a journey through space as well. And so we need a measurement in space. And I'm going to use the electromagnetic spectrum as a ruler. Linейка. Is that right? And now I'm going to show you that it goes from kilometers, which is radio waves, right the way down through meters, millimeters, micrometers, nanometers, picometers. Picometers are there's a small atom down here. Picometers are very, very small. Right, let's go to another slide. We're going to run a film again now, please, if we could. If we click on this image, this is a film, this is a power supply. Can we click? Or does my click work here? Maybe my click works here. Okay, we're going. We're going to make voltage. 10 kilovolts we'll go to. And you see there is no current. And these pieces of metal here look like that. And there is no current. But here is a candle. And so I will ask my assistant to light the candle. There we go. The flame. Now stand back. And now here we have solid, we have liquid, we have gas that is burning, and we apply electricity. And look, there is electric current. And look at the flame. No, it's not blowing. It is electricity that is making that. Okay. Let's turn down the voltage. Just a little. Now, let us blow to make this candle disappear. See? And look, the current has also disappeared. So there is no current, whether is no flame. Let's see what we learn from this. I would like you to click from the back. Could you click? There's some words appear here. Can we see click? Yeah, good. Keep going. To there, stop. Good. Air does not conduct electricity. We saw there was no current when there was no flame. Air is colorless. We see no color from air. We see straight through it. But the flame emits light. It's yellow. And it emits a bit of heat. The flame causes electricity to be conducted. When the flame was there was current. And the presence of the electrical charge that was in here made the gas behave very differently. It made it behave so differently because the flame was bent over, electricity was passing through. Good. Let's see what happens next. Can we click on this film as well, please? Here we go. This is a microwave oven. This is a thermometer. Measures temperature. It says we are at about 30 degrees Celsius. This is a tablecloth. Oh, here is 2 tubes. There were 2 tubes, and there is some water. There is a cup with nothing in it. We take a tube, and we put it in the cup. That bit is easy. Then we take another tube, and we put it in the cup. I'm coming back here to see what it looks like. We're going to put these tubes into the microwave, and we'll put the water in as well. And then we're going to close the door and turn on the microwave. There is no light in this microwave. I took it off, but you can see a picture of me filming it. And you see the gas in the tubes is now beginning to glow. And the color of the 2 tubes is different. And you see also that sometimes it goes out, sometimes it's a strong color. So could we also please click again to reveal some observations on here? Good. And what we've seen is that the microwave is exciting the gas. Oh, not this. Can we stop this now? Thank you. We saw that the intensity of the microwaves varied a little bit in space as it went around. And there are microwaves inside the oven that have a pattern. And where the waves are strong, then the light was bright. Also, the glow, where it is strong, is in the whole of the tube. We didn't see the detail, I'm sorry, but the measurements that I did showed that the tubes do not get hot. The gas is glowing, the tubes are not hot. The water gets hot, but not the tubes. This is science. We're doing experiments. Experiments to say, next slide. There we are. This is another experiment. This time, what have we got? Could we click, please? And information is here. I think, no, it isn't. Okay, well, we click. This is a sphere, a glass sphere. Inside it, there is xenon. And outside it, there is a coil of copper. 3 turns. And here is a power supply that makes electricity at 10 megahertz frequency, 10 million times per second, like that. And that means that it makes a magnetic field in this space, which goes up, down, up, down, up, down, 10 million times per second. When you have a changing magnetic field, things want to make electricity. And that's what happens here. This is electrically conducting. It's an electrically conducting gas. No boundaries inside the sphere, no physical boundaries, but there is a region where current flows, and there is a region where current does not flow. This, my friends, is a plasma. Inside the microwave oven, the gas glowing was a plasma. The top of the candle flame that conducted electricity was very nearly, but not quite, a plasma. So we're understanding a bit what plasma is. Can we run this film again, please? Click on it again, just to run it again. It's very short. It breaks down, and it wobbles. It wobbles around. And I hope you're thinking, why is it wobbling? And maybe you're thinking, well, there's a bit of gas in there. Maybe that gas gets warm. And when gas gets warm, the gas in this room is warm. It bubbles up. So and when it bubbles up, it carries up the conducting charges. And so that ring of current wobbles. So we've done 3 experiments now, and we've seen a plasma. Let's click again, see what happens. Can you please take us forward? Yes, again, on the whole slide, just to take it through to the next slide. Yeah, they've done that. We've done that. Let's go to here, right. So now we say, oh, well, we've seen a plasma, but what really is a plasma? Now, the answer to that has taken me about 40 years to work out, and I still don't really know it. But you can go to a dictionary, which will tell you in a few words what is happening. And this is what you find. Meaning number 1, physiology. Oh, they're the colorless liquid component of blood, which carries the blood cells around the body. That is plasma. I didn't show you that. That's not electrical plasma. The word plasma just means fluid. Next definition comes from the next slide. Let's see if I can make that happen. In physics, it's a gas, good, that has been heated, good, to very high temperatures, and most of the atoms and molecules are broken down into free electrons and positive ions. Electrons have negative charge, positive ions have positive charge. You can also have negative ions, but this is electricity. This is the sort of electricity that made my grandson's hair stand up. Right, so there's that kind of electricity in a plasma. Read on, because there is a 3rd definition of plasma, which is from geology. It's a bright green, microcrystalline quartz mineral. I understand that when they named this mineral plasma, they did not understand what the word plasma actually meant. So this is a mistake, but we live with it. Let us go to the next slide, which says, stick with the physics. Gas, high temperature, atoms and molecules broken into free electrons and positive ions. Let's see where we go. This conducted electricity because there were free electrons and positive and negative ions. And it was their motion towards from one electrode to the other that causes a wind, called an ion wind. But you see there's positive charge, which goes one way, negative charge would go the other way, and that is why the flame does not all go over there. It goes a little bit sideways in both directions. Here we said this was a plasma. This is a torus, a donut shape, or a bagel, you might say nowadays. Or you just say, it is like a life ring when you're swimming. It's got a hole in the middle. And these are plasmas inside the tube. Okay, so we've seen plasma. We've looked at definitions of plasma. Let's go down now from the real world pictures, images, photographs. We're now going into drawing, because this is too small to take a photograph of. Atoms and molecules. The size of that atom is about 100 picometers. That's very small on our scale. Here is the scale with meters and picometers. Down here, this is the picometer, 100 picometer, 1,000 picometer becomes nanometers. So this is small, this is the size of atoms. That's so small we need to refer it to something closer to us. I hope you can see this. This here is a human hair. And this here is a ruler, and this is 6 centimeters to 7 centimeters. Now, I can assure you that that is a human hair, because 5 days ago, I pulled it from my own beard, just for you. So that I could make the point that across here, just the diameter of that hair, 500,000 argon atoms, all the way across. I choose argon because it's an inert gas. It's not too heavy, it's not too light. It's a good representation. 500,000 atoms, that's a lot. 500,000. So what about a plasma? That was a gas. What about a plasma? Well, we break it up into ions. Not all of it, just a small fraction of it. So we get positive ions. We get electrons. And I've got some arrows showing them moving. So let's see why they're moving. They're moving because, of course, it's at high temperature. Well, some of it is. And many atoms are broken up, but not all of them. So let's talk about the speed at which they're going. And here's a point of reference. This is 0. This is speed in meters per second. And this is 1400 meters per second. I want to reference that to something which is more familiar. And here we have a car going at 130 kilometers per hour, which I think is allowed. You can do that. But that's only a very few meters per second. These atoms here, room temperature, they're not even hot. They're going 400 meters per second. So they're going somewhere around here. But they're not all going at that speed. Some are going faster, some are going slower. And we can show what that looks like here. 3 curves suddenly to look at. Let's take our time. The blue curve. This is actually for oxygen at 0 degrees C. And you see that many atoms, most atoms, have got around 400 meters per second. Some are just going very slow for a moment, and then they get banged and they go faster. And some are going, woo, up here. If you make the oxygen hotter, you take it up to 127 degrees, then you move this peak to there. If you say, well, suppose it was a heavier gas, carbon dioxide, CO2, is heavier than oxygen, and that makes it go more slowly at the same temperature. So even at 0 degrees, carbon dioxide moves more slowly than oxygen. But the electrons here, these are very light. These have very low mass and a little bit of energy from an electric field that accelerates them to super high speeds. 1,000 kilometers per second. 1,000 to 10,000 kilometers, this is meters. So on this scale, they are somewhere over here in the center of Lviv. It's a very high speed. And so this is what's hot. In my kind of plasma, not all plasmas, but in my kind of plasma, it's the electrons that are hot, not the gas. And the electrons, hot electrons, can do chemistry. Let's see some of that in action in a moment. This distribution, this shape, was described in physics by James Clerk Maxwell. Did a lot of good mathematical work. He did this when he was working in Scotland in 1860. So on my timeline, we've seen boys being electrified, and now we've seen Maxwell doing this. What else was going on around that time that's connected to plasmas? This is a way of making ozone. Actually, he didn't set out, this is Werner von Siemens, he did not set out in the first instance to make ozone. He was like many people, many curious people, who said, electricity, what can we do? We can electrify boys, we can make hair stand on end. But what happens if we apply that electricity across a gas? What happens to the gas? That's what he was doing. And what he discovered was that when you do that, you change the gas. It doesn't have to be pure oxygen, it could be air. But this is just a way of pushing the air. It's a very simple pump. Pour water in the top and it pushes gas out down here. And we can dry the gas and then it can go here. And inside here, what does it look like? It looks like this. There is an arrangement of 2 glass tubes, one there and one around the outside there, and we put the air into the gap between the two. Inside the inner tube is a metal tube. Outside the outer tube is another metal tube. And now you make your electricity across that and see what happens. And what happens is you make ozone. They didn't probably at that time even know it was ozone. They knew it smelt a bit funny, and they knew that it killed bacteria. And very quickly it was realized this was a very good way to make water purer, to kill the bacteria in water. Now, when you have a really good idea, it lasts. Sometimes when you have an idea, it lasts for a while, but things move on. I can tell you that now, today, 2026, there is a lot of ozone sterilizing, killing the bacteria in a lot of water. Still used today. It doesn't look, the apparatus does not look like this anymore. It looks a bit more modern, shines a bit of metal, but it's the same principle. Right, move on. What have we got? We've got here, look, energetic electrons plus oxygen makes the gas ozone. Now, a bit later on in time, still, we're not getting back to 13.8 billion years. We're still up at this end here. But these are called tubes, lighting tubes. Back in 1800, though, they had big electric sparks. High voltages suddenly break down the air, produce high current, and that can be used, makes things hot. It's those electrons again, but it can make the gas locally very hot. That will melt metal, and it will make metal join together. So that's arc welding, but it makes a lot of light, so it's also an arc light, and sometimes it could still be seen today. Certainly the welding is going on all the time today. And then these tubes here, these are gases. Helium, neon, argon, krypton, and xenon. They're different colors because the color is characteristic of the physics of those atoms, but they're all in tubes, and they are all modeled on the same kind of tube that was designed in 1920, 100 years ago, for advertising. So one way to make money, you don't make a lot of money out of making ozone, you just save a lot of lives, but you make a lot of money out of advertising. So the people who made the neon tube must have made a lot of money. By 1938, it's been realized that the same physics, the same electrical conduction through a gas, a plasma in the tube, if you put a wall around the tube that has got some special chemicals in it, we call it fluorescent materials, but it's oxides, zinc oxide, magnesium oxide, get a mixture of those. And what happens is the light that is produced is actually ultraviolet light, not visible, not so much visible, but the ultraviolet light hits the oxide material, the magnesium and the zinc oxide, and it re-radiates as visible light. We call that fluorescence, so that's a fluorescent tube. 1938. Between 1938 and about 2000, many, many, many big buildings, even in houses, had fluorescent tubes about 1 meter long. And they're about 1 meter long because we have 200 volts, and the plasma needs about a volt per centimeter to keep it glowing. And then somebody had the idea, could we make them smaller, wind them round? And we had compact fluorescent lamps. They come in a moment, wait a minute, they come, too fast, but they come here. In the middle of that, very clever design, atomic physics had been studied, and somebody had said, you know, if only we could make this device that amplifies light. A little bit of light goes in and makes more light come out. And to do that, you need to set up your atoms. The light comes from atoms. You need to set your atoms up so a lot of them are excited, more excited than there are not. That means that they will, given a little bit of a push from light coming through, suddenly out comes more light as these relax from their high energy state. So we need a system of making high energy atoms. One way to make high energy atoms is to hit them with these electrons. We can make hot electrons, hit them into the gas. The gas is a mixture of helium and neon, and you get a laser. Since 1960, a good idea, we still use helium-neon lasers. They're still around. But semiconductor physics, we'll say a bit more about that in a minute, semiconductor physics came along and said, you don't need a gas. We can do this with a solid. We can make light-emitting diodes become light-emitting lasers. And so many modern lasers are solid and not gas. But we still use the gas ones, as I will show you in a moment. Just now, 1990 until about now, these are beginning to be phased out. Very bright lights on the front of motor vehicles contained high-intensity arc discharge. Bright light. That light that I'm looking at right now at the back may well be of this type. But increasingly on motor vehicles, it's a light-emitting diode. Ask yourself the question, how do you make light-emitting diodes? I'm going to give you the answer shortly. What have we got? We've got electrons in the plasma converting electrical energy into light. So, without that ability, without those plasmas, we might be a bit in the dark. But we've got this one too, we mustn't ignore this. Thank you to NASA for the image. About getting back down this line, look, getting back towards 13.8. But back here at 4.6, our own sun was formed. Gas coming together, gravity pulling it in, and it was shining. Now, the interesting thing is that people thought the energy must come from gravity. Gravity pulls the atoms together and they get hot. They become a plasma and they are. And there was a scientist named Eddington who in 1920, perhaps he had seen a neon light, but in 1920 he said, if you do the sums, there's not enough energy in the gravity pulling the gas together to make all that light, the light going out in all directions. So where does it come from? And the answer is, that's not just gas that's hot, that's a plasma. And when you get atoms in a plasma, all hot, even the heavy ones, even the ions are hot here. Then there's enough energy in those ions. When they bang into each other, they can break through the atomic forces that are holding the atoms apart, and they become sticky. Hydrogen will stick to other hydrogen, and neutrons will stick to protons, and you can go from hydrogen to helium. If you wait, you go from helium to lithium. And if you wait, you walk down the periodic table of the elements, building heavier and heavier elements, to oxygen, carbon, nitrogen, and eventually you get to a point where you don't get more energy out, and it doesn't happen. And you have to look to other processes. Now, nuclear fission, that is in the nuclear power stations we have now, takes very heavy atoms and breaks them apart to get out energy. But between the two is this minimum. And once you go below that, then fusing them makes energy. You go this side. Then fission, breaking them apart, makes energy. Oh, so without this kind of plasma, we would be, of course, completely in the dark. Nuclear fusion converts atomic energy into light. We are at the halfway stage, so I want to check how we're doing against what I think are the outcomes of this talk. And it's a talk. I'm talking to you. I'm trying to see you. I'm trying to engage. So please continue to look at me. That's good. Thank you. Because it's not really a lecture. Lectures are a waste of time. This is a conversation. What is plasma? Well, I hope if you knew before you came, I hope I haven't disturbed what you thought. If you didn't know, I hope I've given you some information which would allow you, at the very least, to go to your family, your friends, and say, for about 20 minutes, I knew what a plasma was, but I'm sort of forgetting now. But I can be reminded. Where do plasmas occur? Well, we think we've had them around since people were playing with electricity 100, 200, 300 years ago. But there is the universe, which is also playing around, and that was making stars 4.6 billion years ago, even more, even further back than that. And I tell you that this plasma, some people say it's a state of matter. Solid, liquid, gas, plasma. Just put energy in and that's what you get. So I was asked if I would, in lectures like this, would you call it the fourth state of matter? Well, I said no, I won't. And thank you for saying yes, because you're right, but I'm just going to change the order. I think it might have been the first state of matter, because we had plasmas before we had solids. We had plasmas before we had complicated atoms, before the periodic table. What thing can be done with a plasma? Well, we've shown that we can make light and we can make heat. I'm going to show you some more in a minute. So is it the fourth state of matter? No. But it's a different state of matter. So, second half, 1970s. I was a boy. 1970s, and this sort of thing was happening. Actually, I was quite an old boy in 1970, but never mind. And we've been doing this ever since. What you're seeing here is a gap of about 2.5 centimeters. Any guess as to why it's 2.5 centimeters? Because it was designed in America and it's actually an inch, which is 2.54 centimeters. So we have a gas contained in here. These are two cylinders joined together facing each other. It's like two cans facing each other and a gap between the two. This is a device put in here to sense what's happening. Well, we have some electricity across here. On this occasion, it's 13.56 megahertz in frequency. And looking in, you see there's a region here which is glowing. We call that plasma. We have solid down here. And we've got this region between the two, which is sort of matching the plasma to the solid. There isn't quite so much light coming from there. In fact, the light that you're seeing here is mainly light that's reflected off the wall at the back. So this is sometimes called a dark space. Given what we know already, I'm wondering if you can think, why is it dark? The plasma is glowing, I'll remind you, because there are electrons hitting into atoms. And that excites the atom, then the atom relaxes, because it takes that electrical energy input, and out comes light. So why is this dark? Something must be missing from there. Is there any gas there? Or you try and stop it. The gas will go where the gas will go. So maybe there's no electrons there. If the electrons weren't there, or they weren't there with energy, then it would be dark. And it turns out that the electrons are held away from this region by electric fields, electric forces which push the electrons back, don't allow them to the surface. And so we get the dark region. That's got to turn out to be very important. Because if electrons are being pushed back, ions are being pushed in. For the ions, this feels like a waterfall feels to water. You get towards it, out to the edge of the plasma, and then suddenly, whoosh, lots of energy is gained just in this region here. And that's used in semiconductor processing for manufacturing chips, for manufacturing the circuits that are in your smartphones. Things like this. This is sulfur hexafluoride gas. It's sulfur and fluorine. And the atoms just go anywhere, but the ions, bang, 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 they come in with lots of energy. So much energy they can break chemical bonds. And when they break chemical bonds, and reform chemical bonds, if you could turn this silicon into silicon fluoride, that would be great because that's a gas. And so you could pump it away. And if you have a gap, a protective layer, but a gap, where there is a gap, you will transfer that gap into the silicon, make holes. That is at the heart of semiconductor processing. And silicon is chosen because silicon makes a very nice oxide which can form part of that mask there. And that ability to quickly form an oxide in a controlled way, to be able to grow that oxide thicker, makes silicon a wonder material. And luckily, we've got lots of it. It's in sand. So there isn't a shortage of the silicon atoms, but there is a shortage of the silicon purified, because this silicon has to be made so pure that it's almost unbelievably pure. It is made so that the amount of impurity, the atoms which are not silicon, which are still in there, can be controlled. We can add just a little bit, and that changes the way it conducts electricity. Without that, we say it's a semiconductor. It's not an insulator, it's not a conductor, it's somewhere between the two. You put in a small amount of this impurity, different types of impurity, and you can make it conduct significant amounts. And you can control how it... This is the way transistors are used. This is used for transistors. It's the way that we have made electronics, the electronics resolution. It began before 1970. It was done with wet chemistry, pouring in liquids, throwing them away. But not only is that wasteful, but some of them are toxic. So if we could do it dry with a gas to etch material, we should. And that's what we do with plasmas. Now, I just want to show you this here. Can we click on this film to make this film go? And can you think where this might be? This is a picture, thank you. This is a picture of water, and it's just flowing along. And suddenly, oh, there's an edge. This is a waterfall. And it goes whoosh over the edge, and there's our electromagnetic spectrum showing up as a rainbow there as well, quite conveniently. I took my smartphone, and I reached out over the edge, expensive smartphone, over the edge, and I filmed this so that I could show people in lectures like this. So where did I go to film that? I was passing through. I didn't go especially to film it. But any thoughts, any suggestions? Anybody want to call out where you think that might be? Did somebody say Niagara? You're absolutely right, yes. Niagara Falls. Other waterfalls are available, and they behave in the same way. So that's the energy going into the ions at the surface to do that etching. I'm trying to get to the next slide. Now, could you move the mouse off? Thank you. So we do etching, and what we're going to do now is look at the detail of this for a finished semiconductor device, where you've got silicon down here. This is a millimeter's huge. This is the silicon. We process it to a few micrometers of depth, and then we grow things on top of it so that we can connect to it. There is an oxide layer. There's some metal that's connected to these bits here, but it has to do so down holes. And then we put some more oxide on because we need to insulate it before we put another metal on to connect to a different bit. And all the way up to the top. 3 layers of metal, many more nowadays in sub-chips, all in less than a millimeter of a layer on top of ultra-pure silicon that was etched with a plasma. And when you put these layers on, you have to change their shape as well to make tracks, independent tracks, going one way and another way. How do you pattern those? With a laser? No, with a plasma. Right, so we move on from there. And we get to what happens next. We go through this scale, we're talking about the 1970s through to 2026. What has been happening, what has been of great benefit to you, is that things have been getting smaller. The size of those features that we're etching are getting smaller. The pattern size goes down. It was in the micrometers level, it's now down towards the nanometers level. And how do you do that? It was observed some time ago that that feature size halves every 2 years. Every 2 years they go, well, it was 200 microns. 2 years' time, we'll do 100. And then 2 years' time, we'll do 50. And then all the way down to nanometers. Now, you make the patterns using light, and because light is very focusable, we could choose where it goes. We could put blocks to where it goes, so we can make a pattern and shine that pattern, imprint that pattern onto the surface, and then we can etch with a plasma through the pattern that we've created. But you see, the pattern has to go up getting smaller. Now, it's difficult to make light focus in a size shorter than its wavelength. So as we come down here, the electromagnetic wavelength gets smaller and smaller. We have to, you might have started with visible light, but then you have to go towards the blue light to make your patterns. And now to get down to the nanometer, 100 picometer level, you have to go into this region here, ultraviolet light. Now, I've said you can get ultraviolet light in the fluorescent lamps. You need it more intense than that. You need it very precise. You want to focus it to the best possible size of spot. So we'd like probably to start with laser light if we can. Let's see what has happened. Here's a laser. You can focus lasers very precisely. And you can focus it onto this region, and it makes a plasma in that region. But that light is going everywhere. So watch what happens now. We put a mirror. It has to be an ultraviolet mirror, but we can make them. And that will focus the light over here. Even EUV, extreme ultraviolet light, can be focused here. And now this is in the hundreds of picometer level, where we need it. We can focus it down to that size so we can make small chips. But how did we make this? What's this? I've just said a laser. And remember, some lasers use plasmas. In fact, this is a CO2 laser, carbon dioxide laser, which is it's an infrared laser. It's not ultraviolet, but it packs a lot of energy. It's very controllable because it's electrical, and we can focus it down to make a plasma out of tin. So to make a plasma out of tin, the metal tin, you melt it, little drops come down, you time it, the drop comes down, you fire the laser, and they meet here, bang! You get a plasma of tin, which happens to be, not just happens, it was found to be rich in extreme ultraviolet. So this is the way that we make extreme ultraviolet from a tin plasma focused down here. So we have CO2 plasma, tin plasma, to make nanometer patterns for etching with a plasma. We're near the end. If you're thinking, this is going on a long time, I can't take this. Stay with me a little bit longer. Just to check. Oh, that's all right, yes. Right, stay with me just a few more minutes. Because what's been happening recently, you may have seen news from around the world. There was a lot of media attention given to the Artemis mission, which sent people round the moon, round the back of the moon, for the first time since the 1970s. Actually, the first landing on the moon had that kind of thing in where they went around the back first of all just to make sure it was possible. And they made a film about the Apollo 13 one where it went wrong. But the 1969 one, the very first one where they landed, Apollo 11, I was woken up in the middle of the night by my father. And he shook me awake. And he said, this will be important. He wasn't a scientist, he got the idea it might be important. Come and watch. So in the middle of the night now, what's happening? One small step for man, one giant leap for mankind. Oh, it's kind of impressive. Now, in 1969, another thing happened. In the United Kingdom, it was decided we needed a university that could teach people at a distance. And we call it the Open University. That also began in 1969. We've been doing it every year since 1969, but after about 1970, they stopped going to the moon until just now, and they're going back with the Artemis mission. I'm not sure it's a good idea, because it's our moon, not just one country's moon. It belongs to all of us. I don't really want them mining resources there, taking things away. But that's another story. If you're going to go into space, if you're going to go out to Mars, which is the next thing they want to go and wreck, and ruin, maybe, mine. But if you're going to go there, you can't go there with chemistry unless you've stolen it from the moon, because the materials you need to make the rocket engines work, where do you get them from? Where do you get rocket fuel from when you're several hundred days out from Earth? What you need is an electric engine. Furthermore, all those satellites up there, all the communication satellites that we use for our mobile technologies, GPS, communications, all of those satellites, they're slowing down a little bit. They're dropping towards the Earth. They need to speed up and maintain their orbit. How are they going to do it? Are you going to take chemistry up there? Are you going to put a bottle of gas up to refuel your satellite? No. What you're going to do is you're going to give it an electric engine. And you can make electricity because the sun will shine on you, and you can make electricity. Once you have electricity, you can make a plasma. Once you can make a plasma, and you've got electricity, you can accelerate ions in much the same way as the chemists do. They make a lot of energy and they accelerate gas. We can accelerate ions electrically in a particular direction. Like the candle went in one direction, but spread out. We can do that with the ions too. So that's what this is. They said, let's test this for moon orbiting, for going around the moon. Let's have an electric engine. And I'll show you a bigger picture of the electric engine. There, here, you recognize it. Oh, we've seen that shape before. That's a plasma. There's another little plasma here. This is making a lot of it extra. We're pulling electrons out of there. We're pulling ions out of here. Everything's neutral in the end. And this, we can electrically accelerate and get thrust. It's happening right now in the satellites that are up there. This just happens to be the one that NASA was developing. And I started building it into this talk. And I did a bit more research, and I found that they had decided not to fund this. Too expensive. Okay. But they will probably be developing it for Mars, if not for the moon. So here we have electrons in plasmas doing physics. The physics of push. And the ions, they're doing push too. The electron push is into the gas to ionize it. The ion push is out of the plasma to push that way so that I can go this way. Thrust. Right, time to go back to our timeline. We've got one more thing to talk about in energy terms, just to say that this 4.6 billion years ago, the universe was pulling gas together. Actually, back here it was. Stars and galaxies begin back here. This is quite a late arrival, but stars and galaxies pulling matter together and getting it so hot, so dense with gravitational energy, that suddenly fusion energy will switch on. And a few years ago, actually, started also around about 1920, got a little more realistic in the 1940s, and then even more realistic about 1969, started designing big experiments like this one here, which is called the jet tokamak. And it's a donut shape. You can already get a clue from, do you remember that donut shape of plasma that we had in the xenon sphere? It was donut shaped because it was a transformer. We get a circle of current. That's why this is a donut shape. We get a circle of current as well. This is a person here. That's a person, so it's a big, big machine. Wouldn't fit in this room. And that's for researching nuclear fusion, which we know happens. That's what's going on here, but it's using it to make energy on the Earth. What you put into it, the fuel, you don't need uranium. What you need is hydrogen and deuterium. Deuterium is hydrogen, actually. It's just heavy hydrogen. Oh, you need some helium as well, so put some helium in there. Well, we can get helium. It comes out of the ground. The deuterium and the hydrogen, it's in seawater. You can get it out if you want. And actually, to make something, we can also, a bit of lithium would be useful. Have we got lithium? Lithium atoms around? At the moment, yes, there are. And if you see any lithium atoms, keep them. Because they're the heart of the battery technology that we're using, and they will become the heart of fusion technology if we get to use it. In fact, somebody might have the bright idea of saying to Elon, whatever his name is, those Tesla things, bring your batteries over here, we need the lithium now. You've had your fun. Okay, so near the end, could we click on that one there? This is a slow film, and it is running. You can see from the time clock. It takes 24 days for the sun to appear to rotate like this all the way around. So we're not going to see all of that, but you see these shapes here? And you'll see some activity. Something will blow out from here very shortly. This is a plasma. This is a living plasma. You say, oh, look, it's just being pushed out there. When you get big explosions out, which one's going to happen down here, it ejects mass from the corona of the sun. The corona is this outer layer. And a corona mass ejection, when it travels all the way from the sun, it takes about 6 minutes for light. It'll take about 60 minutes for these particles, and they hit the satellites. And they can disrupt the satellites, and communication can be threatened. So it's important that we look at this. Here it goes. Oh, that's all right. It's going to miss the Earth. It's going sideways. It's the ones that come from here that we need to worry about. But the weather satellites that we have now in geostationary orbit, so the sun, they go around like this exactly with the Earth, so they're always looking down at the same piece of ground. They're looking down at the Earth, looking at the weather, reporting back. It's also looking out at the sun, looking at the space weather, because the early warning we can have from that will allow us to protect the satellites. Science in action. Well, here we go. Let's go from that. I put it to you now that without plasmas, we would be in the dark. Literally. Because there wouldn't be a sun. And figuratively, because we would not have the information that we have at our fingertips right now. How did we do? Do you think for more than 20 minutes now, you've been able to follow what a plasma is, and you might be able to tell somebody else? Do you think you might be able to say, yeah, well, is that one a big glowing one in the sky when it's not raining? That's there, we know about that. And those lights, some of those bright lights may be from a plasma. And, that smartphone device. Do you know the chips inside your smartphone device don't just see one plasma. They see almost 100 different plasmas in their manufacture. So without them, we really would be in the dark, wouldn't we? That's doing a useful thing with a plasma. But we mustn't forget, Werner von Siemens did it 200 years ago, was making ozone, which we still make with a plasma. Useful things. And so let's deal with this thorny one. We haven't really put this one to bed. I said 13.8 billion years, beginning of the universe, Big Bang. Do you know what happened after 2 or 3 minutes? I don't know whether you know, it's a rhetorical question. Don't answer. I'm going to tell you something. I don't even know how they measure time back then, but anyway, it is said that after about 2 minutes, there were protons and there were electrons. Do you need more for a plasma? I'll get started with that. So, is plasma the fourth state of matter? No, it's the first state of matter. This solid, liquid, and gas, recent. They will come, they will go, plasmas will stay. Thank you very much. I think I might be able to answer a question or two, or talk about something. If somebody had a burning question they wanted to ask that they thought, you didn't say, criticize, that's good. I like positive feedback. I'll take negative feedback. If anybody's got anything they'd like to ask, then I'm looking for somebody who's an organizer who said, stop it, don't do this. I know you'd like to ask a question.
I have a question for you. In school physics education, what do you think is more important, learning formulas or work with real instrument, doing experiment? What do you think?
Nice question, thank you. Is it worth doing real, or is it better to do real experiments or just sit there and learn formulas? Get it from a book. I mean, getting things from a book, we get those at our fingertips off our internet these days very easily. Do we need to know them? It's actually quite good to know them inside out, because then you can tell when the internet is not telling you the entire truth. Aided by artificial intelligence or artificial stupidity, they can tell you the wrong thing. But then, if you don't test it, if you don't do experiments, it doesn't matter how good or elegant the theory is, it must be testable. So my answer is, well, maybe you agree with me, but yeah, we should do practical investigations. We should use instruments. We should understand how they work. We should question how they work. And when I teach in laboratories, I do two things. I mentioned one of them in a workshop yesterday. I tell you that one of them is you put one hand in your pocket if there is anything electrical around, because that way you save your life. You don't want electricity across your heart. So one hand in your pocket. And the other thing is, don't trust. Don't just take it on trust. Question everything. The only exception I have to that in my laboratory is an oscilloscope, which has been designed very well by very clever people, and I sometimes trust that. Thank you for your question. Oh yes, gosh, can I pass that?
Okay, so what actually formed a Big Bang? Like, we know that plasma was there always. Then why did it explode? Like,
I wasn't there. I was not there, and I haven't studied it in great detail. So, as I was advising our colleague here, don't take it on trust. I should really say I just don't know, but I could go and find out. Give me a moment. Now, I would go and read. But I do know this, it's a lot of energy. That's what makes it go out. It's energy, it's a big bang, it's an explosion, a concentration of energy, and energy will spread out. And when it does, when it totally spreads out, you get something which is called thermal equilibrium. Everything is balanced, everything is at the same temperature. And there's a microwave background of radiation in the solar system, of 3 Kelvin temperature, because it's all spread out. And when you spread it out and share it out, there's only 3 Kelvin of temperature, not very much. And so you spread all this energy out, eventually you get very little. Thermal equilibrium is very, very dull because nothing happens. It happens and it unhappens, and it happens and it unhappens. It's not very interesting. So we like concentrations of energy. That one, 13.8 billion years ago, was a particularly large concentration, and we are living with the consequences. But we've been living with plasmas almost as long. There's a second question down there.
hi. Thank you so much for the lecture. I have 2 questions for you. Yes. So I would like for you to give the microphone back after you answer the first one, if possible, of course. So the first thing is, if plasma is so common in the universe, and why does it feel like it's something so unfamiliar or exotic to most people? Because coming from a biological background, I only knew the first definition, which is a part of the blood, basically. And for people who are not physicists, what is the biggest misconception about plasma? So why is it so unfamiliar, and what is the biggest misconception? Why no one talks about it? And then there is another question.
Part A of question 1 was, why is it so unfamiliar? Why is it relatively unfamiliar? Well, it's not just me that talks about them. There are other people, but there are not enough of us, clearly. We'll have to try harder. There's an awful lot in life that is hidden from us, and we discover it if we go looking, but if we don't ask the questions. If we're not curious, then you won't find out. There's an interesting question, association. You talked about the blood plasma, and it was the blood has got particles in it, different types of particles. Plasma has particles in it, different types of particles. So in 1928, an American called Langmuir, who is also famous for some chemistry that he did. He got prizes in chemistry and in physics, I think. Then he said, but this thing has got particles in it. It's like blood plasma. So let's call it plasma. He applied it to my kind of plasma. That was 1A. What was 1B? Just remind me quickly. Oh, misconceptions, yes. What are the main misconceptions about plasma? Nice question to have to answer, because it is this, that they are not all uniformly hot. So the sun's ions and electrons and any rare atoms that are there, unionized, it's almost all ionized, they're all at the same temperature. They are in a kind of thermal equilibrium. My kind of plasma, which is the one that makes semiconductor chips, that's not in thermal equilibrium. People say, oh, well, that's hot. How hot is that? And if you ask some people, they will say, oh, about 20,000 Kelvin. 20,000 Kelvin? How do you keep that in a box, it's in a vacuum box, but how do you do that? But don't worry, the gas is quite close to room temperature. It's the electrons which are very hot. They're at 20,000 Kelvin, the gas is at 300, 400 Kelvin. So that's a misconception, that they don't all have to be the same amount of heat. Okay, how are we done? I got one here, I'll come over there, and then I'll try to look over here.
Thank you for your time and supporting our country. I have a fantasy question. Is it true that the future of space travel belongs to plasma engine? And will we use them to travel to Mars?
Yes. Very good question.
Thank you. So, according to science, is it possible to get like electrons with high speed, to get beta particles from plasma, to turn regular elements like iron to radioactive elements like isotopes of iron?
Thank you. Nice connection there to beta particles, which are themselves electrons, the same bits of negative charge. They have the same charge to mass ratio as electrons, so we call them electrons. They are indistinguishable. Can we get them at high enough energy in order to transmute the elements, to get into the nucleus? If you want to do that, don't do it with an electron, because an electron is very light, so it doesn't carry that much kinetic energy. Also, the nucleus is really quite small, quite hard to hit, and it's got positive charge on it. And you might say, well, won't that suck in the electron? No, it sucks it into an orbit. And the mechanics of it would rather have it orbiting. If you want to get in and affect that nucleus, hit it with neutrons, not charged particles, so they won't worry about the protons that are there, and they're small enough and carry enough energy to get here. So that's what would be my recommendation. But never take that as oh, I won't bother then. Just think about it, and maybe you find there's a loophole. I've made a mistake. Now you know how to do it with an electron. And when you do, send me an email. Thank you. Now, may I go to the back just a bit? Otherwise, we'll be here until midnight.
Thank you for such a wonderful lecture. I'm here with my friends, and we are studying physics in university, and we would like to hear maybe some advice from you, because we would like to become great scientists.
Physics is fun. If it isn't fun, you're not doing it right. Physics is hard. If it isn't hard, you're not doing it right. So please have some hard fun. Now let me go to the back here.
Thank you. You mentioned that microchips, these transitioners, are getting twice smaller every 2 years, right? So, and you used ruler also to compare that. Is there a limit to which we can reduce the size?
Thank you very much. It gives me a good opportunity to throw in one more point. I told you that my beard hair had 500,000 atoms across. By the time we get down to the extreme UV scale, the hundreds of picometers, we're talking nanometer scale, yes. We're talking about 50 atoms across those features. Not 500,000, but 50. Well, there's going to come a time when the physics of your semiconductor, which is to do with bulk solid, it's quantum mechanics happening, but in bulk solid, and you get energy bands and so on, that's not going to work if you've only got 50 atoms. That applies to millions of atoms, not to 50. So it's getting down to the quantum scale. But that's all right. We're also working on things called quantum computing. People will want to go on making things small and smaller still. And at the moment, the technology for building quantum gates, some of it uses plasmas too. So I'm not worried. I've still got a job. Thank you for your question.
Oh, thank you for your lecture. Since you mentioned quantum physics, does plasma behave differently on the quantum scale, and is it researched?
Oh gosh, you're so inspiring. I mean, plasma is like the solids. Plasma is a bulk thing. We talk about we model it as a fluid of electrons and a fluid of ions. So if you get onto the quantum scale where you've got one electron and one ion, that would be the ultimate limit, I suppose, of a neutral plasma. That's an electron and an ion. But plasma has, its characteristic is that of what we call collective behavior. So if we got the whole room, if I say to you, don't do this, but if I say stand up and you all stand up, or one person stands, the next person, and so on, that is collective behavior. If you're talking about an ultimate quantum system of an atom, it's not collective anymore, it's just on its own. Okay, does that do? All right, my eye has been caught over here and somewhere. Go on, yes?
Thanks for this great lecture, and can I have one question? You mentioned multiple like lasers and lamps that use plasma, so you can like tune the wavelength of them with just changing what plasma from like what elements it's constructed. Did I understand it correctly?
Yes, the radiation from lasers, the emission from gases comes from atoms. And it's the characteristic of the energy levels of the atoms that gives you the color of the light, the wavelength of the radiation. If you want something like extreme ultraviolet for my tin plasma to make those very small features, then you need to go right down into the core of the atom where the energy levels are quite much closer together to get those kind of energies. And that's why tin was there. But yeah, you know, when the periodic table was first being worked out, people were working these patterns, what are they all about? There was quite a lot of time for saying, oh, I wonder if there ought to be one there. There's an atom there, there's good these characteristics, there's an atom here. What about something in this gap? And one of the things that was identified in that way, I believe, this would need to be checked. If anybody is recording this and putting it on the internet, I'm saying, I don't know, it's a half memory, but I think antimony might be one of those things. Or somebody said there ought to be something in the periodic table about here, just below something else in the patterns. So it's a very rich resource that we have in our atoms. I hope they're in, I mean, we've got 120, is it, or something like that, different elements. That's enough to go on for now. We don't need more. I think you can do amazing things, but you might not know which atom is the one that you want for a particular task. You have to look. Okay, now, how am I doing? I want to be sharing the room. Any question? There's one over here.
Thank you so much for not a lecture, but a conversation. So I have a question. I'm interested about environmental application of plasma. So I've heard about technology like plasma gasification, like treatment for the disposal of hazardous chemical, medical, and municipal solid waste. So I'm interested in, do you think it has really potential for practical use, or it can be way too expensive compared to chemical methods or something else?
Very nice to go into this area, thank you. Environmental applications. Yes, with plasma, it isn't the solid and the liquid and the gas, it's broken up, and in the end, on the Earth, it will recombine. Out in space, it would stay there, but down on the Earth, our plasmas eventually recombine. So I like to think of them as well as being matter on its way somewhere else. It's been something, it comes through a plasma, and it'll go somewhere else. So could we take hazardous materials, break them up with the plasma, and have them joined together in a different way that is not hazardous? Yes. And then you very sensibly go on and say, but would it be economical? That is going to depend on a lot of things. I have colleagues, international colleagues, particularly strong in the Netherlands, who are looking at removing carbon dioxide, breaking carbon dioxide up, or building long chains of carbon, a bit like fossil fuels, but made from carbon dioxide, reversing that process. Can we do it? Yes, they're finding some interesting ways of doing it. Is it worth it? Don't know. If you ask the is it worth it question too early on, it's a don't do it, don't do it, don't do it. And so you need to encourage it. Have a go. Who knows, you might discover something. But listen to the messages that you get from it. And if it's proving too expensive, look for a different way. Don't give up on the idea, but look for a different way. Thank you. Oh, yes, sir. Sorry, did I wake you up?
How can I make a plasma at home?
Health and safety. Well, you can make plasmas, I am told, in the microwave, where you have an energy source. You need something to be also providing the particular gas, localizing the gas to do it. I am not recommending this. Again, we might be being broadcast on the internet. I am not recommending it. I will tell you what I have seen. I have seen some people do some very silly things in microwaves, and they did involve plasmas and grapes. Google it, learn from other people's mistakes. There is no need to do it yourself. The safe way to do plasmas is in a laboratory with somebody who is curious and has one hand in their pocket. I see another question there, and I will come to you afterwards.
Hello. Firstly, I'd like to say thank you for this incredible lecture. So my question is, can global warming on Earth occur from plasma changes on the sun, and how to avoid this?
Thank you. Well, the global warming is the warming, the heating. Some people like to say global heating because it's gone beyond the warming bit. It's not getting very hot. It's a combination of factors. Some of it is anthropogenic. Means it's been created by humans. But if you look through the ice cores back in time, you see that we've been through cycles where it's been warmer, it's been cooler, it's been warmer. How much of that is a result of the sun? The sun's there, it's been shining. Has it triggered any of this? No, it's tolerated it. It's maybe helped to create the environments of the swings that happen. I think if you're concerned, and everybody should be concerned, not worried, but concerned about global warming, I think the big thing to do is wasting energy. We've got to look at that wasting of energy. The big thing is to stop wasting energy. Use it to advantage, but don't waste it. So don't make plasmas do things that you don't need plasmas to do. And sometimes, you know that picture of the fusion reactor, the jet fusion reactor, the Taurus. They've invested an awful lot in that. And I do sometimes wonder if you had spent that money making windmills, might we have got the energy that way? But depends how long into the future you want energy. And we must always think about, I mean, it's a good point, let's build on that. You must always think about this effect on the environment and leave the world as a better place than what we started with. And some of the things we do with plasmas, most of the things I think are in that direction, but probably not all of them. Well, I will dwell on that. Thank you. There was a question here. I'm sorry, I'll come to you afterwards. If we've still got time.
Okay, thank you so much. So we are really grateful to have you here today. And my question is, like, we know that science is developing currently and always developing, and we have a lot of research now. But my question is, what can be the next realm, like next area where we can apply plasma? Like we have today like smartphones with these chips, which was very interesting to listen about. And what can be the next area to apply plasma to it? Thank you.
Thank you. What a nice question. If we had a crystal ball, and we could look at the future, wouldn't that be good? I don't know. I'll wait. I'll get there. But what is being done right now? What is at the cutting edge? What is mentioned? Will it take off? Plasma medicine. Using plasmas to, if you can localize the plasma, you can localize the creation of molecules. Reactive species of oxygen and nitrogen, very good for killing things inside the body and so on. I have seen some colleagues, this was probably 10 or 15 years ago, proposing and demonstrating the use of a plasma to sterilize, that's what the ozone does, but to very locally sterilize, wait for it, the inside canal in a tooth. When you get quite old, your teeth have this problem, you have to have them mechanically cleaned. Oh, it's awful. I had five. But doing it with the plasma, would you try it out on a few people before you offer it to me? But plasma medicine, it is used for wound healing, sterilizing wounds where the skin has been cut and exposing it to an atmospheric pressure plasma. Plasma at atmospheric pressure is relatively new. We've been doing it for 25, 30 years in research terms. The plasma of Siemens making ozone, because he was using atmospheric pressure, but then we found as physicists, you say, well, let's make it easy. Get away the complications. Oxygen, hydrogen, water all at the same time. No, pump it all out. We'll just put argon in there. No chemistry. An awful lot of plasma work was done like that. And they got more complicated. You come to atmospheric pressure. If only you can make atmospheric pressure plasma. I'm working on an atmospheric pressure plasma now that what we want to do is to measure very thin films to see whether or not the coating on a metal has got a hole in it. And we can use a plasma to get current to flow through that coating. So I'm doing that. I'm not the first to do it. I might be the first to do it in this particular industry. I've already thought of a way of doing it without the plasma, but they don't want that. They want to do it with the plasma. Okay, so we'll have a go. So there will be things. Where you need electrons, there shall be plasmas. Now, was any... Yeah? Wait a minute, is this number 2? Yeah. Anybody else got a... can I go to this person first? Yeah, I'll take care.
Okay, thank you. Can we use actually plasma engines in our atmosphere to run airplanes or drones, or they work only in vacuum?
Thank you. More thinking going on. Very good. Well, yeah, we talked about atmospheric pressure and the complications of atmospheric pressure. It's very collisional at atmospheric pressure. In order to get thrust, you want to be able to push, like that, and to get the acceleration of ions, the electrical acceleration of ions, then you need no collisions so that we can get that energy in within an electric field of a certain strength. If you're going to have collisions, you need stronger and stronger fields, so it's more and more difficult. But there are types of thruster which are available, which just make the gas hot. Although I said my kind of plasma is very often the gas is cold, there are ways of making the gas hot. That's what happens in welding when you want to melt metal. So making a thruster that makes the gas hot and just expels it, that does work. and you can get thrust at near atmospheric pressure from that kind of device. Will it be worth it? How will it compare? I don't know. The cost, the additional overhead, as we say, with having your electricity. Are we talking batteries? If they're batteries, the voltage needs to be high, so there need to be circuits alongside it. I don't know, to be explored. Maybe your future. Yes.
We'll probably have one last question because of the timing, but still we have one more question.
Okay. So when the plasma falls from the atmosphere of the sun, where does it go, and does it solidify instantly?
The plasma that's blown off from the sun sets off on a long journey, which it will never complete, because it will go across the universe. But the universe is also growing, so but it's spreading out. So it will stop being a plasma, as described here, as a collective phenomena, once it gets far enough apart. And there are numbers you can write down and say, well, after this number, this amount of spreading out, it will no longer be classed as a plasma. But that's where it goes. It goes past the Earth, some of it entrains with the Earth, some of it gets caught up in the magnetic field of the Earth, and those charged particles accelerated down towards the Earth, down the magnetic field at the poles, produces the aurora. Have you ever seen the aurora? Yeah, it's beautiful. We got it in England a few weeks ago. First time I've ever seen it. Absolutely amazing. Glowing gas, electrons. Not a plasma, but from a plasma. There we are.
Yeah, that's probably it for right now, because we have no more time. Give a round of applause to Mr. Nikolas, to Professor Nikolas.